So, so for the second part of the of these tutorials, I will try to tell a little bit about the numerical methods of the computational methods to solve these mean field game systems. So let me just copy, write down again the system. Okay, so this is the system that we are dealing with. And let's also just keep in mind the cost that an individual agent is minimizing. So here I'm assuming that we're in the case where we're controlling the velocity. So this is the cost of the individual agent. Okay, depends on V and rho. And so I'm going to be abusing the notation by interchangeably using rho for the measure or its density when it's absolutely continuous. So I'm going to do this a lot. Okay, so as I mentioned before, so this dependence, or actually let me write it here so that everyone can see. So this dependence of the terminal cost function and the Lagrangian on the density, it's called the mean field interaction, because it encodes the interaction between the agents, between the population and an individual agent. And if we consider different types of interactions, we get different types of mean field games. And this is how we model different scenarios. So let me give you one example of this Lagrangian, which is one of the most studied ones so far. And it's given in the following way. So x v rho. So it's equal to some Lagrangian plus some coupling term that depends on rho. So this f is not f from the dynamics before, and because now I'm just going to use the case where we control the velocity, there is going to be no confusion, okay? Now, if we assume that this Lagrangian is given in this form, let's calculate what is the corresponding Hamiltonian. So h bar is x v rho. And so we have that it's supremum minus and because now this part doesn't depend, so f part doesn't depend on v, we can take it outside of the supremum, and what we'll get is that it's and if we make the notation, so we denote this by h xp, okay? So we'll get that h bar is going to be h xp minus fx rho. And so this system will become down and I'll comment on it. Okay, so the first equation will just become hx grad phi is equal to f of x rho, because I just replaced h bar according to this formula. Also, because this f of x rho doesn't depend on p, what I have here is that dp h bar at x p rho is simply dp h xp. And so if I replace dp h bar here by just dp h, then I'll get this equation here. And so this is one of the most common mean-field game systems that appear in the literature. And it's called, so this is called the separable case, and it means that we can separate the dependence on the density into a standalone function that doesn't depend on V. Okay, and so going back to Ryan's question about like control theory, what is the way people try to solve this in engineering applications? So often you don't have this separable structure for the applications that they are interested in. That means that here I cannot do most of the cases analytic calculations, and I cannot write a formula for the Hamiltonian. And so this case is somewhat, I wouldn't say easier, but more apparent to study from a mathematical point of view, because you can write the HJB equation, and the properties of the Hamiltonian are, you can infer some properties of the Hamiltonian. Okay, so yeah, so it's this case, and now so from now on I will consider this case only, and I will not consider that general case, and different types of mean-field games will depend on different choices of Hamiltonian and different choices of functions f and g here. Okay. So let's see what are possible choices that we can make. So we can divide it into two groups. So local couplings. So I forgot to mention that sometimes people also call it coupling, mean-field coupling, because the first equation is an HJB equation, the second is a Fokker-Planck equation, and if this F would not be there, this wouldn't be a coupled system, because we could just solve for phi and then just solve the Fokker-Planck separately, so they're decoupled, and that's when you have this term here, we have the coupling. So the case of local couplings, this means that this F that depends on the distribution actually depends locally on the density of that distribution at point x. So for instance, it can be, let's say, logarithm of the density at point x, at location x, or can be some power of the density, or in general you can take some function, one variable function, and apply it to density. Or we can even take a two-variable function that also depends on x and on the density. So somehow this means that if we go back and look at the action here, which can be rewritten as LZV plus Fx, F0 d, sorry, S so we see that the way the population affects the cost of the single agent is given through the density along the trajectory. So precisely the density of the agents at that point, wherever the agent is currently. So that's why it's called the local coupling, because it only depends on the on the position there. And the same comments also apply to the terminal cost or the terminal coupling. Okay, so we can have the same kind of choices. So logarithms, you can have also coefficients, powers, this type of thing. So any function of the density.
Sorry, I mean, a local coupling is only when you depend on the function of the density?
Yes. Yeah. So, okay. Now the next class of couplings are non-local. And examples are something like this. So let's say F, where again I'm using the notation X. And so now the way agent at position X interacts with the whole population is given through this integral. So basically there is an interaction weight, we can call it an interaction weight, and we're calculating the aggregate effect of players at position Y on the position on the player at position X by just accumulating this cost along the population. So you can think, for instance, you can think about xy as being, let's say 1 over distance, for instance. And then this would mean that if other agents are close by, then you're penalizing this behavior. So you want to be far from each other. Okay? So the point here is that if I want to calculate f of x rho, the information of rho at point x only is not enough. I need to know rho across the whole population. Okay, and yeah, so these are called non-local couplings. Of course, any non-local coupling, I can add here some local coupling, but at the end of the day, it's going to be non-local because I will need collect all the information from the population. And yeah, so these are the two cases. There are also cases which are called congestion models. That actually do not fall in this separable structure, but I'll just write it down for completeness. So we assume that the way so the way we're given L hat is some Lagrangian, some cost, multiplied by the density to some positive power. Density at point x to some positive power. So why is it called congestion? Because given the same control v, so if you're moving with exactly the same speed, you pay more cost if you are in a denser area. So that's why it's called a congestion cost. But for this one now, the Hamiltonian will have h bar as a more complicated form, and I will not study that one here. So these are the main classes of problems. And okay, so now the next question, before even we try to solve numerically this problem, we need to understand what is actually a solution, right? So what are the difficulties that we face here? So, okay, this is a Hamilton-Jacobi equation, and if epsilon is 0, for instance, we know that there are no continuous solutions, and we have to use the theory of, for instance, viscosity solutions. But the problem is that if here, imagine...
They're not continuous.
What?
It might not be continuous.
What?
It might not be continuous. You said there are no continuous solutions.
Oh, sorry. Yeah. So there are no smooth solutions. Yes, I'm sorry. Yeah, there are no smooth solutions. So, and the natural theory for Hamilton-Jacobi equations is the theory of viscosity solutions. But there is a problem here, and is the following. So let's assume that this f of x rho is equal to, so let me, rho beta of x for a second. Now, a priori, rho is a density, so it's an L1 function, right? And a priori, we don't know whether it's actually continuous. So then if we're considering this Hamilton-Jacobi equation, then h bar, this Hamiltonian, may not be continuous. And so if the Hamiltonian is not continuous, then the theory of viscosity, it's hard to do the theory. Special care has to be taken of. So this is the difficulty with local couplings. And the notion of solution in these cases is non-trivial, and it's a hard problem from PDE perspective to understand what is the notion of weak solution, etc. And there are a number of works by Cardalegui, Porretta, Alpar. He has done a lot of nice work here. People trying to understand what is the appropriate notion of solution, and I cannot tell it basically in one sentence, but just it's some sense a distributional solution. Let's put it in this way. Although this is a nonlinear equation, but there is some way to define a distributional solution. But if you are interested, I can give you later references and etc. So, just wanted to say that when you have local couplings, the notion of solution itself is very hard to understand, and therefore numerical methods are also not easy to design and prove convergence and this kind of thing. So that's one case. Now, for the case of non-local couplings, let's imagine that these kernels K and S are smooth kernels, let's say twice differentiable. So, so let me erase this. So let's say K is C2, and then what happens is very similar to what happens for convolutions, right? So if we differentiate this expression in X, then derivative falls on the kernel. And if that derivative is actually smooth, then no matter what we choose for rho, it's an L1 function. It can be even measured. I could integrate it against the rho. If this is smooth, this integral will be a smooth function of x a priori, right? Which means that if here this function f is actually smooth, then if I choose rho to be in L1, the right-hand side will be a smooth function. And then I'm in the case of viscosity solutions, and I can understand the solutions, at least for the first equation, in the viscosity sense. So this is the key difference between like non-local and local couplings, is that if you have such kind of things, you get for free basically a nice regularity on the right-hand side. If you don't have this, you have to work it out. So you have to prove things, and in general, the type of solutions that you get, I think, are rho in LP spaces and phi in Sobolev spaces, but yeah, something like that. Whereas if you have non-local couplings, and of course under additional assumptions on convexity of Hamilton, so whatever you have for the Hamilton-Jacobi equation, you take exactly that setting, and then you take smoothing operators, then you already know that, okay, for this case you have, for the case with epsilon, you have smooth solutions, you have semi-concavity estimates, and etc. For the case when epsilon is 0, you have continuous viscosity solutions, but again, you have semi-concavity estimates, and etc. So this is a simpler setup from mathematical point of view. This is harder setup from a mathematical point of view. Do you have some questions so far? Okay, so but if we think about numerical methods, let's try to think about numerical methods and discretizations. Then in the case of, so let me write it down. So, yeah?
You might be planning to talk about this, so I can wait if you are. But even just forward-backward systems, are there any general approaches to dynamics?
I don't think so. Maybe fixed point, but that's very, yeah. No, I don't think so. What?
Do you have uniqueness when you have?
I will talk about uniqueness. Yeah, I will. So discretization is simpler for local couplings. So although mathematically the local case is harder, numerically to discretize it, it's simpler, because if we have a discretization, so let's say we have a grid and we have a discretization for rho, then it's obvious how to discretize this f of x rho. You just put the value of the grid there, right? It's just there. So from the numerical point of view, local couplings are way easier to discretize. I mean, not way easier, but more straightforward, let's say. Whereas if you have a non-local coupling, then you need to discretize this sum, right? So you need to, at each node, you need to add all other nodes. So there is a matrix operation here. And if you have a grid, so you have a number of grid size operations at each grid. So in the worst case scenario, you have a grid size square number of computations that you need to do, right? So that's why, because theoretically it's easier to study non-local couplings, and in fact in the seminal paper by Lasserie and Lyons, they actually develop the theory of viscosity solutions for the case where there is a smoothing operator. And that's why the first papers on numerical methods which were, so among others, so H2, and Camilli, and I think Silva had some papers. Yeah, I may be missing some, but because the theory was backed only in the case of non-local couplings by that time, most of the numerical methods were actually analyzed in the case of non-local couplings. So if you want to show that discrete problem converges to a continuum problem, you need somehow to have good properties of the solution on the continuum level, and that's why people were concentrating on this case. Although they were calculating some examples with local interactions, and they were getting good results. So once the PDE theory caught up somehow, so people started proving existence results and the uniqueness results for local couplings. Basically, almost exclusively, all the numerical papers switched to local couplings. So, because there was a backup from the theory, so we're looking at problems that have solutions and they're well behaved. So, and you can see when you read the papers, you can see this transition, because this is a headache to discretize. On the other hand, from modeling point of view, this is a much richer class of interactions, because, for instance, you can model like heterogeneity, so you can put different. So if you have some coupling like this, let's say rho x to some power, this means that it's a homogeneous coupling, right? It doesn't depend on the direction around you, the way the population acts. So this is like something like very similar to modeling pressure in fluids, right? So that's why it's interesting, but from modeling perspective, this gives you richer structures, and like you can have heterogeneous interactions in different directions, etc. And towards the end of the talk, I will show you some examples. And so running a little bit ahead, so we found a way actually to basically discretize this type of problems, so solve numerically this type of problems in an economical way. So without basically doing direct grid discretization and calculating all these sums. So and I will show you that. Okay, yeah. So that's the setup. Local problems somehow simpler to discretize, but harder mathematically. Non-local problems simpler to study from mathematical point of view, harder to discretize. Okay, so let me see if I, yeah. Okay, so now let's jump into the actual numerical methods, how to solve these problems. So the first, or one of the first actually, so we can divide it into two groups, the numerical methods. One is general purpose, which is somehow using the structure of the equation, but applies to a general class of problems. And this is basically Newton's method. And this was done by H2. Yeah, but basically, yeah, let me rewrite. And the way they solve the problem, first they discretize the Hamilton-Jacobi equation, and for that you know that you need to use special kinds of discretizations for Hamilton-Jacobi equations, because if you do it in a direct way, you'll have instabilities. So basically you take a discretization for the Hamilton-Jacobi equation and the discretization for the Fokker-Planck equation, but there is one crucial thing that you need to be careful. So an observation is that the second equation is the adjoint of the linearization of the first. So if we linearize the first equation, take the adjoint, we get the Fokker-Planck equation. And so when we're designing the, let's say, a numerical scheme for that problem, it looks something like this. So we discretize HJB, right? And then the Fokker-Planck is the, basically, let me write it in this way, which is JB prime. So we linearize it, and then we take the dual. Okay? So we differentiate the first equation in the discrete variables of the phi, calculate the dual of that, and that's going to be the discretization for our Fokker-Planck equation. So why is this important? So it's important because when you're studying theoretical properties of the continuous problem, for a priori estimates you're using this dual structure, and that's why you want the a priori estimates to hold also on the discrete level. So you're basically implying the same kind of identity on the discrete level, and then you get estimates on the discrete level as well. And so once you discretize this whole system, the way you solve it, you're using Newton's method, basically. Okay? So you have a system of equations, and you just apply Newton's method. So what are the advantages and disadvantages of this approach? So, well, the advantage.
Time and space.
Yes. Yeah. Yeah. It's a hard structure. It's time and space. So the HJB runs backwards. Fokker-Planck runs forward.
The Newton's method in particular, so you discretize everything.
Yes. Yeah, so you discretize everything.
Dimensions.
What? The examples I've seen are two-dimensional. So with time, it's 3. Yeah. So the good thing of their analysis is that actually they show that this discretization converges to the solution, and actually they show it later with Alessio Porretta and Ajdu. They show that this convergence holds also for the case of like hard case. So you define a weak solution, etc. And so once you have this, actually, in some cases you can see that the discrete system that you get is correspond to some convex optimization problem. So you can like use the fact that this solution converges to actual solution, and then but solve it not with the Newton method but with convex optimization method. So, but let me tell you some of the difficulties of applying Newton's method there. So first of all, it works when epsilon is positive, because that's when you have smooth solutions, and that's when you can guarantee that the measure is actually the density is positive, and that's important. And although they have shown that it works actually for small values of epsilon, the convergence is much slower. Another problem is that we have a constraint here, which is rho should be at least non-negative, right? So when you do a Newton step, it may happen that you pass this threshold. So you may get solutions that are negative. And then the way around this is basically to restart with a smaller time step. That's one approach. And second approach, introduce some regularization parameters and do a continuation method. So this is one of the most common ways that Newton method is used. You solve it for some case which is simpler to address, and then you incrementally change the parameter, and for every other case, as you take as initial point the solution from the previous iteration. Because Newton method converges very fast when you are near the solution. Okay, so that's one thing which can slow down the convergence, and also it's not a global method, right? Like a convex optimization where you start from anywhere, you will arrive to a solution. So these are some of the limitations of this method. So the one that I want to talk about is based on convex optimization. And for that, what we need to see, yeah.
So your discretization will start with time.
Yeah.
Short for the other one is backward.
No, what I meant is, if I'm not mistaken, so I may be saying something not so correct, but it's the same flavor. So you can add here some kind of like regularization term, like lambda phi, right, which will regularize the whole system. And when lambda is a big positive number, the system is better conditioned, so you can find the solution easier. And then you take lambda equal to, let's say, 1, and then 0.8. And then for 0.8, you use the solution that you got for 1 as your starting point, and go down until you get to 0. So this is what I meant, yeah. Okay, so so the methods that I want to talk about are based on convex optimization, and this has to do with the potential games that I mentioned in the first part. So what we are going to see is that in some cases, this system is equivalent to a convex optimization problem. And so instead of solving this system, we'll solve the convex optimization problem. So let me write the statement. And so assume that there exists a functional f that depends on rho, so that little f is the variational derivative of this f, and this is the not so perfect L2 derivative that Wilfried yesterday was talking about. So it's the variational derivative, and so the way we define it is as follows. So I'm being very formal here, so I will not give any conditions, etc., but things can be done. So let's say so this converges to so it's just a directional derivative, okay, or variational derivative. And also we assume that G is also a variational derivative, and that similar definition holds for that. Let's also assume that f and g are convex in rho, which is not the optimal transport convexity, but the simple convexity. So Okay, and the similar for G. So just the usual convexity. Then the statement is as follows. So let me write it for the case epsilon equals to 0 because it's simpler calculation, but exactly the same calculation works also for positive epsilon. So let's number this, let's say MFG. So MFG is equivalent to T to the following optimization problem. So we take this functional, which is given the following way. So we integrate density against the Lagrangian, plus we take the antiderivative, more or less, of f, and then for the terminal cost, we take this capital G, and we minimize for all pairs rho and v that solve the continuity equation with the given initial data. And I'll do this calculation to convince you that. Okay, so this is the statement. So, so if we have this setup, we call, so these are potential mean-field games. And this is reminiscent with what I was telling before, that for some games, which are potential games, Nash equilibria correspond to a convex optimization problem. Yeah, Ryan, you had? Oh, okay. So let me show this calculation, and then we will, so formal calculation. Okay, so well, we do the standard thing, which is introducing a Lagrange multiplier. And let me just have this to get the signs correct. And so we can write this infimum as infimum in rho v and supreme in phi. And this is not a coincidence that I denoted by phi. So let's copy this. And I'm going to add this constraint here as using this phi as a Lagrange multiplier. Okay, and plus rho t. Okay. And then we do the, actually, let me do it here. And then we do, we interchange basically inf and sup. So just to save time, I'll do it here, okay? So that thing is equal to yeah, so all the things that I'm doing right now are formal, but can be made rigorous. So now, first, let's optimize with respect to V here. And actually, what I'm going to also do, I'm going to integrate by parts here so that I have integration against rho. So, so this is equal to supramin phi, infinin rho v d. So dt phi t, so plus g t, and then minus, there are some boundary terms, right? So and let's make the following observation, because rho x0 is rho 0 x. For this term here, I'll just write rho 0 of x. And I have this. Okay. So first, let's optimize in V here. And the terms that contain V is this one and this one, right? And so what we'll get is that infimum in V Lxv plus grad phi dot V is equal. So we recognize here the Hamiltonian, right? So this is going to be minus h x grad phi, right? Because I was defining the h as the sup of the negative of this. And the V that is minimizing here is, so I'll need this later. So let me do the changes here. So I got rid of the V, and I have here minus rho times. Okay? So that's one step. Now the next thing that I'm going to do is I'm going to optimize in rho. And then, so inside of the integral, I have this term here and this one here. So let me isolate that that part, and we'll have minus okay. So this is the part with rho. And now you again recognize here the Legendre transform, right? And this is equal to f star right? So that's and also, and additionally, the optimality condition gives me the derivative of f with respect to rho is equal to right? Because it's like I'm differentiating this thing with respect to rho. Yeah.
Is there noise on this?
No, but if you have a noise, that it's going to be a bilinear form there, which is just it's not going to change anything.
So okay, so at this point though, is this already looking good to you as far as convexity, or you haven't derived that?
So for convexity, I'll need one more little step, which is this trick of going through the flux, but I will explain that later. Yeah. So so I get this equation. On the other hand, we had, I mean, it's behind here, behind this board. We have that this is equal to f of x rho, and so we get the HJB equation. So we get the first equation. Okay. Yes. Now, additionally, we have that the solution must solve the continuity equation, right? And so, where should I write that? Okay, maybe here. Okay, so we have the continuity equation, and V is equal to this, so the continuity equation becomes equals 0. And so this is the second equation. So when we write this, basically the Lagrange multipliers here, and we write the optimality conditions, we get exactly the system that we had. Oh, I forgot to mention the boundary conditions, but the boundary conditions are just exactly the same calculation, but for rho x of t. So we do exactly the same calculation, and we get that. But let me write actually, so if once we are done with this optimization problem, let me write what do we get. So we get an optimization, so let me erase this just to, yeah. Let me write it down. What do we get? And this is important. So we get supremum in phi. So this here gives us, so there is minus t t minus so if we optimize with respect to rho and replace these expressions by f star and g star, the way I was writing before, we get this dual optimization problem. Okay, so this was a primal optimization problem, and this is the dual optimization problem. So phi, so the good thing about this is that we got rid of rho, right? This is an unconstrained optimization problem for phi. And if we have convexity assumptions on f and g, then we'll have that this is a convex problem. And so we can solve it by convex optimization methods. And in this form, actually the most commonly used method is ADMM, which is, you can find it in paper by Benamou, Garlet, and there is also an article, Sant'Ambrogio.
So this is the minus of this. This is the convex problem?
Yes, I'm sorry, yeah. So this is a concave problem, yeah, if we write with minus, yeah, it's becoming a convex optimization problem. And I want to point out, so make one comment which is connects back to,
I mean, so f star must be monotone or something.
it's convex, yes. So yeah, but f, once you have that f is convex, its Legendre transform is also a convex function. So one point that I want to make is that the success of these methods is based on the fact that you have to be able to calculate this f star and g star in an analytic way. Otherwise, there is no use in this method. And local problems, when you have like, so example. So let's say is some function, local function of the density rho, and let's assume that this function f is monotone, one variable monotone function. Then you can construct f rho as the integral, and you take the antiderivative of this f, and you construct in the following way. And yes, you can f star, let's give a name, I don't know, like new. You get so in the case when you have a local coupling, it's easy, and let's say you have a power, a logarithm, or one of these cases, it's easy to calculate the dual. And that's why all of the further calculations that you're using with ADMM and etc., they can be done efficiently. Okay, and this is important because now, if you have a non-local coupling, you can't calculate this thing.
It's just fine.
What? 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 So sorry.
So it's unconstrained.
It's an yeah.
It's just fine.
Yes.
Rather than the
Yeah. So that's the trick also for the like ADMM. Somehow you write a constraint problem as an unconstrained optimization problem. That's kind of the trick. It's an unconstrained problem in the dual variable. Okay, so I'm not gonna go into details of how you apply the ADMM here, or yeah. So for the sake of the time, I'll just show you the trick how to make these methods work when you have a non-local coupling. Okay, so that's what I want to show. And again, I want to mention that you cannot calculate this analytically when you have a non-local coupling. So let me show you exactly the problem that I'm interested in. Yeah, so just to close this part is that once you write it as a convex optimization problem, there are like a plethora of algorithms that you can apply to solve this type of problems. And so the difficulty is somehow to transfer the problem into a nice convex optimization problem. That's the trick. So let me just for the last 15 minutes or so, I'll just show you a way to solve this for the case of like non-local couplings. And so let's assume that we have the following case. So let's assume that here so phi xt is g of x. So I take a simple cost function at the end. I don't put coupling at the end. And I put some kind of non-local interaction there, where k is a kernel. So yeah, again, if you try to apply these methods directly, you'll encounter difficulties. So we show a way how you can actually circumvent that. And the idea comes basically from a simple observation in Fourier analysis, which is the following. Let's assume that kxy is a convolution kernel. And let's say we're in a periodic setting, although I will not need it later, but just to explain the idea, let's assume that we're in a periodic setting. Then this right-hand side will be as follows. Now let's assume that k is actually a trigonometric polynomial. Again, later I will not need that, but that means that in the Fourier space k has finitely many coefficients, then it's 0, right? And so no matter what I take as a density, I calculate this convolution. This is going to be a polynomial, again a trigonometric polynomial at most of degree k, because all the coefficients of rho after some point, they don't matter. So then, a priori, I know that this expression here is a polynomial, and I can expand it in a basis, and the coefficients is what I'm going to search for. So let me do it for in general case. So let's assume we have some basis of functions fi, which they don't need to be, in fact, orthogonal or whatever. And let's assume that kxy can be approximated or can be written in some cases as a sum like this, okay? Then if I calculate the integral this is going to be equal to fjy dy. And so after rearranging things, okay, so if you have your kernel has that form, then no matter what you choose rho, it's going to be expanded in fi. So if you have finitely many functions here, right, then this right-hand side will be expansion of this form. And now what I'm going to do, instead of searching for rho, I'm going to search for these coefficients ai. And if I manage to approximate a convolution with a small number of coefficients, then I'll reduce the dimension of the problem because I will need to find just a little number of coefficients.
You don't need it to be a convolution.
It doesn't need to be convolution.
And you don't need it to be orthogonal. Just
Yes.
yeah.
And yes, and I'll show you. It connects nicely with the actually kernel methods in machine learning.
Multi-D, I and J are multi-D index.
Yes. Yeah. So so I make these ansatz because I know that it has to be the case. I make these ansatz and I say, okay, so this right-hand side should be a sum AIT FIX, and FIs are the bases that I choose. So this is I know beforehand, and let me denote by so given A, let me solve the following HJB equation. So I give you A, and I solve this HJB equation backwards in some way, and I produce phi A x t. So let's make the following assumption that K is actually, this kernel K is actually symmetric, which means that the matrix K of these coefficients is also symmetric. And let's assume that, that it's invertible, which is consistent with the well-posedness theory of mean-field games. So this is positive definite symmetric matrix. Then we can prove the following theorem. So the solution of the mean-field game is given by the following optimization problem. So so we take this quadratic term. So this is just, let me write it in an expanded way. So let's say Rij are the coordinates are the entries for k minus 1. And so this is going just to be, okay? So what is the idea here? The idea is that we model, basically we put all the non-local interactions, all the information about non-local interactions into these finitely many coefficients A1, AR. And we're saying, okay, instead of solving the mean field game system, finding phi and rho, we're going to find these coefficients A and phi. And it turns out that these coefficients, they satisfy a variational principle. So they are not just random coefficients. They solve a certain kind of a specific variational problem, which is given like this. Okay, and in general, so once you have this principle, you can devise various methods of solving the problem. And I think one of the most interesting applications of these things would be solving these mean field games in high dimensions in Lagrangian coordinates, so in the control theory perspective. So why is that so? Because let me explain why is that.
This is your work. You should give a reference to that.
Yeah, okay, I'll give a reference. Yeah, so we did. Yeah. So this was yeah, it's me and Saud. So why is that so? Because we can write. Yeah, I think I can. So we can write phi I of x0 by the just the definition of the, because it's a value function, we can write it as infimum integral from 0 to t L z dot plus right? So let me denote zx is the point. So for each point, we have that there is this representation. And of course, if I know these coefficients A, then the trajectories will depend on these coefficients, right? So let's say someone, and by that I mean Stan, Jerome, Alex, and others, had these nice methods of solving the problems, quick solution methods for the HJB equations. There is a quick way of generating optimal trajectories for given A's, right? So let's say there is a quick way to generate Zx that also depends on A. Then the partial derivative, so it's going to be the variational derivative with respect to coefficient AI. By the envelope formula, basically, it's equal to, so phi I x0 is going to be fi z x t. So once you know the optimal trajectory, then you know how to calculate the gradient of this thing with respect to A. You just need to calculate the function fi at the point on the trajectory.
This will all be done in high dimension without
Yes.
grid.
Yeah.
There's no grid here.
Yeah. So then what you can do, you start with some A, you generate a trajectory, or even approximate trajectory. You don't need to find it perfect. So the way we were solving here, we were doing just one gradient descent step. But let's say you generate this, and then you correct your trajectories, you correct your interactions by just doing a gradient descent step on this, where this part is quadratic, very simple, and the derivative of this part, so is just going to be integral rho 0x dx. So in fact, you can sample from your trajectories and just calculate expectation, and you are done. You know the gradient direction. Yeah.
Let me say this is really a big deal. This enables you to divide dimensions without grids.
Yeah, so that was, yeah, so with Alex, for instance, we're trying to push that case. With CTIN, actually, we saw that it works very well also for if you're looking to Eulerian case. And yes, the main idea is that, and here actually is not important now what kind of control problem you're solving here. So I don't have the theorem for a very general case, but I suspect that once your control problem is well set up, then you can basically approximate optimal trajectories, adjust them, adjust them, and then you will get convergence. So this way you kind of decouple the mean field and the optimal control problem. So if you have a quick way of solving optimal control problem, you should be able to solve this type of mean field games by just correcting the trajectories once in a while. And normally, these coefficients AI, they converge faster because they're kind of aggregate quantities. Like they're not local quantities so that you have oscillations. They're aggregate quantities, so normally they converge faster. And yeah, let me show you some interesting examples where these methods work. So we did it with CTIN, Matt, Wu-Chen, Stan, and yeah, I think I'll need the projector to show you some examples. I didn't have time to talk a little bit about how to build these kernels and connections with like kernel methods in machine learning, but I mean, I can show you later if you're interested. So okay, here what we're trying to do, we're basically have these two parameters, lambda 1 and lambda 2, which are controlling the spread in each of the directions. So the higher value of lambda, the more spread will be the swarm of the population, okay? And so with this approach, in fact, we can incorporate those lambda coefficients in the basis functions, and that matrix and that K matrix will be always identity. So those are trivial calculations overall. So let's see what happens here. Oh, oops, let me go back, and I want to comment about that. So you see that, okay, so this first case where the lambda 1 and lambda 2 are equal, this is more or less like transportation problem. They kind of go in a transported way. So here, lambda 2 is very large, so we want a lot of spread in x2 direction, and you see that the swarm is actually spread in x2 direction, whereas in x1 direction is the same. Here, we're spreading in all directions, and here, again, in x1, there is a lot of spread, and there is no spread in the other direction. And this is how the density behaves. So you can see that somehow, yeah, you see this is like the agents try to basically encompass a large area. Okay, so another types of kernels that you can use, these are Gaussian repulsion kernels, and you can use here sigmas are different in different directions. And you can incorporate in your problem obstacles, which are basically no issue for the way we formulate the problem is no issue. It's just a linear term in the convex optimization problem. And here you can see again, like, so sigma, again, controls the spread. So the larger sigma, the more spread, the less spread are the agents because it penalizes the close by agent, and you see that when you basically have no strong repulsion, the agent just goes through the corridor. There's no problem. When you actually impose a spreading, you see that, okay, they have to go through the other corridor because, yeah, they split. There is a congestion cost. And here, in this case, we see that, yeah, you can have even more split. In this case, we see that sigma 1 is large, which means that in x1 direction, they don't care about congestion, but they care about the congestion in this direction. So you see they're going like in a queue. So it's prolongating the trajectories because we want that. And you can control this easily. Also, it's no problem for this optimization to include like moving obstacles. And so you can see like they're avoiding all these things. And then again, you have different parameters there. And let me see. Yeah, so you can also have regimes. So you can say, okay, the agents interact in this subregion, or they don't interact. And so you can see that, for instance, here, we said, okay, here there is a full interaction, so everyone interacts with everyone. But here we say, okay, the agents that are here, they do not interact with agents here. And you see that they are getting congested along this line, because it's, yeah. And you can do these things basically by playing around with the bases, and the complexity of algorithm doesn't change at all. And this is one example that we computed from Ajdu's paper, one of the first papers on numerical methods. There they had some kind of non-local operator, which is given by an inverse of a differential operator. And we know that we can solve it using the fundamental solution. And it's a torus, so Fourier spaces, perfect setup. And these are the images, yeah, that we got, and they're exactly the same as in their paper. And in fact, here we're solving a first order equation, whereas there it's a second order. So this is more degenerate equation. Let's see. Yes, and that's it, I think. Yeah, that's where I'll stop. Okay, thank you.